All right, so now we're going to go over octal, or base 8, which of course has 8 possible digits, 0 through 7, with a weighting factor of 8. So as they show here, there's a table with some decimal numbers and their binary representations and then their octal representations. And if you notice in the octal column, they number from 0 to 7, but then once they hit 7 and go past that, they have to roll the next column over to a 1 and then start numbering at 0. So when we think about binary to octal, it's actually kind of convenient how binary and octal, base 2 and base 8, work together. Converting between the two is actually pretty easy because it turns out that you have 3 bits in binary that can represent exactly 8 different numbers, 0 through 7. So when we convert between the two, let's just start with binary to octal. Let's say our binary number is 010110. Well, to convert this to octal, all we really need to do is group these in groups of 3. And actually, let me just add on a 1 to the beginning of that. So the whole number is 11010110. We start on the right side and we group everything in 3s. So we'll group this together, we'll group this together. Now we notice, and the reason I wanted to add this is to show an example of an uneven group, but there are only 2 bits here, but that's okay. We can fill the beginning with leading zeros here and make it exactly 3 bits. Because by adding a 0 here, we're not changing the value of this at all. We're just making it easier to organize. So we can group that set of bits as well. And now we just go through each set and we convert individually. We convert these into their decimal equivalent technically, but octal is a subset of decimal. 0 through 7 is a subset of 0 through 9. So we can just figure out each set of 3 bits individually what number they represent. So this first number here, if we remember our weights of 1, 2, and 4, 1 times 2 is 2, 1 times 1 is 1, you add those together, it's 3. So the second set of bits would be a 2, and this third set of bits would be 4 plus 2, which is 6. And there is our octal conversion. And this would be base 8. So going the opposite direction, just as simple. Let's just say 265 is our octal number, base 8. Well, now we can just break each single digit out into sets of 3 bits. So we'll start with the 2. We break out the 2. Its binary equivalent is 0, 1, 0. Breaking out the 6. 6 in binary is 1, 1, 0. 5 in binary is 1, 0, 1. And there is our complete binary number. So binary and octal play really nice with each other. Converting between the two is pretty painless. However, when we go to decimal, that's where we have to go back to our other methods. If we're going from octal to decimal, we'll start with that. We'll go octal to decimal, and we'll say, let's see. Let's just do a 1, 7, 2, base 8. And we want to convert this to decimal. So we need to, whenever we convert things to decimal, we need to use our multiply by weighting factors method. So we need to figure out our weighting factors for each of these columns. Each of these columns in base 8, remember that it's always just the base number to a 0 here for the first column, 8 to the first for the second column, 8 squared for the third column. So this 8 to the 0 would be 1. 8 to the 1 would be 8. 8 to the 2 would be 64. So those are our weights, 1, 8, 64. So now we just multiply these numbers by their weights. 1 times 64 is 64, of course. 7 times 8 is 56. 2 times 1 is just 2. And then we add up the numbers, and we get 122. So 172 in octal is 122 in decimal. And then the other way, going from decimal to octal, remember when we go from decimal to anything else, any of the other bases that we have covered, we have those two methods of successive division and subtracting weighting factors, which I will go over first. But then we have a third method that I'll get to that plays off of the relationship between binary and octal. But first, we'll do the successive division. So with successive division, of course, we take our starting number. We'll reuse this number, 122. So and I'll split the page again. For our decimal number 122, base 10, for successive division, we're just dividing, when we're doing binary, we were dividing the number by 2 every time, but now we're in base 8, so now we need to divide by 8 every time. So we'll take our starting number, 122, and we are going to remember to keep our remainders all in a column. We're going to divide 122 by 8, which turns out to be 15 times. It doesn't divide evenly, so there is a remainder, but it can go into 122 15 times. And 15 times 8 is 120. So our remainder would be 2. 8 can go into 15 only once. 8 times 2 is 16, but that's greater than 15. So 8 can only go into 15 once. So it'll be 1 with a remainder of 7, because 15 minus 8 is 7. That's the remaining. And then finally, we divide 1 by 8, which 8 is greater than 1, so we're left with just a 0 with a remainder of that 1. And then we just go in reverse from bottom to top and take these digits. 172 is our octal equivalent. So then the other method would be subtracting weight factors. So to do that, similar to what we did with base 2, we're going to write out our weight factors for each column, and we're going to stop when our original number, 122, can fit into that number. So we start with 1, then we go to 8, then we go to 64, then we go to what is it? 512. Well, 512 is the first time 122 can fit into that number, so we'll stop here and we'll disregard that column, and we're going to start with the 64 column. So then we write out our original number, and we think, how many times can 64 go into 122? Yeah, it can only go into 122 once. So we'll put a 1 down, and we'll have to subtract off that 64. We're left with 58. Now we move over to the next column. How many times can 8 go into 58? It's 7 times. 8 times 7 is 56, so we'll subtract off that 56. We're left with 2. How many times can 1 go into 2? It can go in exactly twice, and we subtract that off, and we get a 0. And once we hit 0, we're done, and we just take that number there, 172. So those are the two methods that we've already done with base 2, doing it for base 8 instead. We just have to divide things by 8 instead of 2, or, you know, our weighting factors for each column are multiples of 8 instead of 2. But that's really the only difference. The methods are similar. So then there was that third method I mentioned, and it plays off of the relationship between binary and octal. Binary and octal, as we saw before, play really nicely with each other. So what we can do, because sometimes, especially, you know, with big numbers, it might be difficult to, you might need a calculator to figure out some of these, you know, multiplications and divisions and stuff when we're working with 8s. But when we're working with 0 or 1, it simplifies things a lot. So depending on the situation, whatever's easiest, this is just another method that you can do to go from decimal to octal. We can take our decimal number, and let's just keep going with the 122 decimal. And we can convert it to binary first, because converting to binary is a little bit easier using, you know, zeros and ones. And then we'll convert that binary into octal, because it's pretty easy to go from binary to octal. So first, we'll take our 122 and we're going to convert it into binary. So that means we need to use one of those methods. Let's just say we'll do successive division. We can do successive division. So we'll start with our number, and we're going to divide by 2 every time, because we're trying to get a binary number here. So 122 divided by 2 is 61, with a remainder of 0. Divides evenly. 61 divided by 2 is 30, with a remainder of 1. 30 divided by 2 is 15, with no remainder. 15 divided by 2 is 7, with a remainder of 1. 7 divided by 2 is 3, with a remainder of 1. 3 divided by 2 is 1, with a remainder of 1. And 1, we can stop here. I mean, we could divide by 2 and get 0 with the remainder of 1, but we can kind of just skip that step, because we know once we hit 1, we could just carry that 1 over to this column here, and then we can collect all of our digits here from bottom to top, and then write them out. 1, 1, 1, 1, 4 ones, and then 0, 1, 0. So there's our binary number, and then we can take groups of 3 now, because 3 binary digits can represent an octal digit. So we'll just take, starting at the right side, take this group of 3, and take this group of 3, and then here's a 1 by itself, so we'll just pad it with 2 zeros to make it even, and there's our third group. So then this first group, 0, 0, 1, is just a 1. This second group is 1, 1, 1, which is 7, and then 0, 1, 0 is 2, and that is our octal number. So that is converting with octal, or base 8. So here are some more practice problems. I will again allow some time, a short little delay, to allow you to pause this video if you want to try these yourself now, and then I will come back in a few moments to show you the solution. All right, so first problem is they want us to take 1, 0, 1, 1, 1, 0, 0, 1 in base 2. So this binary number, they want us to convert it to octal, base 8. Pretty simple. We just do our groups of 3, group them together, pad with a 0 here to make this an even group of 3, and now we just translate 0, 1, 0 is just a 2, 1, 1, 1 is a 7, 0, 0, 1 is a 1, and there's our octal number, 271, in base 8. Now, problem 2, they want us to convert 624, base 8, into binary. So, again, it's kind of just the same thing in reverse. We're going to do the 6 first. We're going to figure out what 6 is. 6 is 110. 2 is 010. 4 is 100. And there's our binary number from Octal. Now, the third problem that they gave us, they have the number 326 in base 8. Actually, let me get a different pen. So, actually, I'm just going to go ahead and this Sharpie might bleed through a little bit. It's the only pen I could find. 326 base 8 is our number. They want us to convert it to decimal. So we can do that by multiplying by our weighting factors, right? So we know that the first column is weighted as a 1, the second column is an 8, third column is a 64, right? So now we just multiply. Once we have our weights written out, we multiply. If we take 64 times 3, we get 192. 2 times 8 is 16, and 6 times 1 is 6, and we just add those up to get 214 is our decimal number. So then moving on to hexadecimal, this is base 16. So of course it's going to have 16 possible digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then we don't really have numbers in our Arabic number system to represent anything 10 or greater. So we have to pull from the alphabet, and we're using A to represent 10, B is 11, C 12, D 13, E 14, and F 15. So basically 0 through 15, but we're using A, B, C, D, E, F for the numbers 10 and greater. The nice thing about hex, similar to octal, it plays really nicely with binary, in that 4 bits instead of 3 can represent a single hex digit. Actually represents all hex digits, or a single hex digit can be represented by 4 bits. And then of course, if you use 2 hex digits, you have 8 bits total, and 8 bits are what we familiarly call a byte. 4 bits are a nibble, so half a byte. And here's just a table of decimal numbers, their binary equivalents, and their hexadecimal equivalents. And of course, you see in the hexadecimal column counting from 0 to F, and then when it gets past F, it rolls over the next column to 1 and starts numbering at 0 again in the first column. So in terms of conversions, binary to hex and hex to binary, similar to base 8. We're just grouping things in 4s now instead of 3s. So if we have we'll start with binary to hex. We'll just say that number there for an example. We just group things in 4s. So we take that group of 4, this group of 4. and we just convert them individually. So if we remember our weights being 1 in base 2, 1, 2, 4, and 8, this number would be 8 plus 2 plus 1, which would be an 11. But we can't, so we need to convert that 11 into our hex digit, and the hex digit that represents 11 would be B. So we would say B is the first digit. And for the second digit, we see that this number is just a 2, so we just write down a 2. So B2. And then in reverse, if we were to take that same digit, all we have to do is break out each individual digit by itself into groups of 4 bits. B would be representing 11, so our binary representation of 11 would be 1, 0, 1, 1. 2 representing 0, 0, 1, 0, and we just combine the 2, and that's our binary number. So pretty easy going between binary and hex. They play really nicely together. Hex to decimal, however, and decimal to hex, we're going to have to go back to our methods from before. So starting with hex to decimal, we'll keep using B2. But going from hex to decimal, we need to multiply by our weight factors. And this time in base 16, we're saying the first column is 16 to the 0, which is just 1. Second column is 16 to the first, which is 16. And then if we only have 2 digits here, but if we were to continue, this would jump to 256, I believe, or 16 squared for the third column, and so on. But for this number, we just have 2 columns, so we just need to worry about these 2 weights. So we just multiply these out. B represents 11, as we said, so it's really multiplying 11 by 16, which would be 176, and then 2 times 1 would be a 2, or actually I should write it here so that we can add them up, 178. So that is hex to decimal. If we want to go from decimal to hex, we need to use one of our 3 methods, because similar to octal, because hex and binary work so well together, we can use that third extra method. So first I'll actually go with the successive division method. So for successive division, we are going to be doing the same thing that we did with octal and base 2 binary, and we're going to be dividing by 16 instead of 8 or 2 like before, but the method is pretty much the same. So we start with our 178 decimal from before, and this time we're going to divide by 16 now and keep track of our remainders like we did before. So if we divide 178 by 16, we get, so 16 can go into 178 11 times, but 16 times 11 is 176. So 178 minus 176, that gives us a remainder of 2. And like I said about, when we get to the point in this method where we get a number that our base number cannot fit into, so 16 cannot fit into 11, so we can actually just take a shortcut and stop here, move that 11 over to the column, the remainder column, And then we, again, go from bottom to top, take the digits and write them out. 11, however, has to be converted into a B first. So we write down that, but then we carry over the 2, and there's our hexadecimal conversion there. So then there's the subtract weight factors method, where we write down our weight factors for each column until we reach a number in which our original number, 178, can fit into it. So our weights were, if you remember, 1, 16, 256. 256 is the first column 178 can actually fit into. So we'll stop here. We're actually going to ignore that first column. We're going to go to 16, the column 16. And we're going to take our number, 178, and we're going to ask ourselves, how many times does 16 go into 178? And the answer would be 11, or B. And we subtract off that amount then. 16 times 11 is 176. So we're left with 2. And we go to the next column. How many times can 1 go into 2? It can go into the 2 exactly 2 times. We subtract that off. We're left with 0. We hit 0. Now we're done. So then it would be our hexadecimal number. And then the final method, using the relationship that binary and hexadecimal have, we can just convert 178, and we'll just reuse the subtracting weight factors method, but for binary, or base 2. So we write out our weights for base 2, 1, 2, 4, 8. I have to rewrite those because I'm running out of space, but 1, 2, 4, 8, 16, 32, 64, 128, 256. There we go. So we hit 256, which is what 178 can fit into, so we can cross that out. We're going to start with 128. So how many times, now we think, how many times can 128 fit into 178 once? So we'll put a 1 down, and we'll have to subtract off our 128, which would give us 50. How many times can 64 go into 50? It can't. It's bigger. So that's a 0. How many times does 32 go into 50? It goes in once. We subtract that off, and we are left with 18. How many times can 16 go into 18? Once. Subtract that off. Got 2. 8 can't fit into 2, so that's a 0. 4 can't fit into 2, so that's a 0. 2 goes into 2 once. Subtract that off. We hit 0, so we know we're done. So the remaining columns can be filled in with zeros. So now that we have this binary number here, we can group everything in groups of 4, starting at the right. So we take this group here, and then this group here. This most significant group of bits is 8 plus 2 plus 1, which is 11, which is B in hex. And then this set is 0010, which is just a 2, and there's our hexadecimal number. So here are some more problems. I'm going to, again, delay for a little bit and let you work on these on your own if you would like to, and I will come back in a few moments with the solutions. Okay, so for the first number, they want us to convert this number in base 2 into hexadecimal. So we just group everything in 4s. There's a group. There's a group. 0, 1, 1, 0 is a 6. 1, 1, 0, 1 is 8 plus 4 plus 1, which is 13, which if A is 10, B is 11, C is 12, D is 13, and there's our number 6D. Then they want us to convert A9 to binary. So we just do the same thing in reverse. We break out A. A represents 10, so how do we make 10 in binary? It is 1, 0, 1, 0. And how do we make 9 in binary? It's 1, 0, 0, 1. And there's our binary number. Next, they want us to convert 2A6 in base 16 to decimal. So they want us to go hex to decimal, so we need to do our multiply by weighting factors method. So we need our weighting factors for each of these columns. There are 3 columns, so we'll need 3 weight factors. Of course, be 1, 16, and 256. And now we just multiply each digit by its weight factor. 2 times 256 is, whoopsie. So 2 times 256 is 512. 512 plus A, which is 10 times 16, so it's 160. 6 times 1 is 6, and we just add all these up, and we're going to get 8, 7, 6, 7, 8 as decimal. And then finally 498 base 10 decimal to hex. So for this, we're going to have to use one of those 3 methods of conversions. Let's go ahead and use, it seems like a bit of a large number, so I'm actually, and because I covered the other methods in octal and binary, I think what I'm going to do is use that shortcut method for converting this into binary first and then binary into hex, which is relatively easy. So actually I'm going to convert this into binary using one of those other 2 methods. And for this one, I think I'm going to do the it's kind of big, so I'm going to do the successive division method. So let's do that. So starting with our 498, we're going to divide by 2 and note the remainders. So for our first operation, divide this by 2. You get 249 with a remainder of 0. It's an even number, so there's no remainder. And then divide 249 by 2, we actually get 124 with a remainder of 1. And then if we divide 124 by 2, that would be 62 with no remainder. 62 divided by 2 is 31, no remainder. 31 divided by 2 is 15 with a remainder of 1. 15 divided by 2 is 7 with a remainder. 7 divided by 2 is 3 with a remainder. 3 divided by 2 is 1 with a remainder. And once we get to 1, or once we get to a number that 2 cannot go into, which is, it can't go into 1, we just carry that 1 over there. And then we just take all of these digits and write them out from bottom to top. And so that would be 1, 1, 1, 1, 1, 5 ones. And then 0, 0, 1, 0. And we want to get to hex, so now we just group these bits up, groups of 4. and we'll have to pad this one with 3 zeros to make it an even 4. So now 0, 0, 0, 1 is just a 1. 1, 1, 1, 1, 1, 1 is 15, but we represent that with an F. And then 0, 0, 1, 0 is just a 2. 1F2 is our final hex number. So that takes us to BCD. This is the last system, binary coded decimal system. So think of BCD as like a hybrid of decimal and binary. So each of the 10 decimal digits, 0 through 9, is represented by its 4-bit binary equivalent, exactly 4 bits. So it's a little bit easier than decimal to binary, and you'll see why. But to get from decimal to BCD, pretty simple actually. You just convert each decimal digit to its 4-bit binary code, and then just move on to the next decimal digit, convert that to 4 bits, and then you just convert each column in the decimal number to its 4-bit equivalent. And all of the conversions will be exactly 4 bits for each individual digit. So you'll always end up with a number of bits that is a multiple of 4. And then BCD to decimal is just reversing the process. You group everything in groups of 4 and write out the decimal representation of those 4 bits. So actually, I'll do an example first before we get to those problems. So let's just take our previous example, this 678 up here. Let's take that decimal number, and we want to convert 678 to BCD, binary coded decimal. Actually pretty simple, because all we have to do is convert each single digit into 4 bits. 6 converted into 4 bits is 0, 1, 1, 0. 7 converted into 4 bits would be 0, 1, 1, 1. And then 8 converted into 4 bits is 1, 0, 0, 0. And then we just combine all those together to get our full binary coded decimal number, BCD number. And then the reverse, if we have 0, I'll start with a 1, 0, 0, 1, 1, 0, 1. I'll just use that number, it's simple. So this binary number here, we want to convert it. There would have to be is leading 0 here actually, because we need it's always going to be even groups of 4, right? So this number is what we can convert from BCD into decimal by just grouping things into 4s like we did with hex, except really the only possibilities are 0 through 9. Now here's the tricky thing. The number I wrote here actually is not valid, and you'll notice this is fine. Okay, this is just 4. This, however, is 8 plus 4 plus 1, which is 13. Think of that as a garbage number. It's not allowed in BCD. You would never see this number in BCD. So actually, if I wanted to make this a valid number, I would be able to, let's just say, convert this 1 here to a 0. So now we have 1, 0, 0, 1, which is 9. And that is a valid BCD number. 4, 9. And if we were to, if we were to take the number 49 and convert it into BCD, this would be the set of bits. So that takes us to these questions here, and I will go ahead and allow for time again, and then I will come back with the solutions. All right, so for the first number, we have 496 base 10. I'm going to convert this to BCD. So all we have to do is break out these numbers individually. 4 would be 0, 1, 0, 0. 9 would be 1, 0, 0, 1. And 6 would be 0, 1, 1, 0. And that is our BCD number. They give us the number, this BCD number, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, and the subscript is BCD, indicating it's a BCD number. They want us to convert this into decimal, so all we have to do is group everything in 4s. There's a group, there's a group, and then there's a group. So now we convert this group. 0, 1, 1, 1 would be 7. 0, 1, 0, 1 would be 5. And then 1, 0, 0, 0 would be 8. So our final number in decimal is 758. And then finally, the other number they gave us, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, BCD. They want us to convert this to decimal. So we group everything in 4s. This group of 4 would be 6. This group here would be a 4. This, however, oh, there's that problem again. This would be 8 plus 2 plus 1, which would be 11, which is a no-no. So this is actually an invalid number, or an invalid BCD number. So here's just a table of numbering systems, basically showing representations of decimal 0 to decimal 20 in all of the different numbering systems that we've covered so far. All right, so then finally, just to touch on what ASCII is, it stands for American Standard Code for Information Interchange. It represents alphanumeric data, letters, numbers, various other symbols too. It uses 7 bits, although the extended ASCII code uses 8 total bits. But the regular old ASCII is 7 bits long. And you should also probably get used to using 8 bits regardless. You know, the final bit, the leftmost bit, would just be a 0. And you really only care about the last 7 bits, but it's a good habit to think of ASCII characters as full bytes, so that you can think of it in both, you know, not just binary, but hex or even octal sometimes if you really want to. But usually the ASCII codes are represented either by decimal or by hex. And because there are 8 bits, or, you know, we're considering 8 bits for each ASCII character, each character can be represented by 2 hex characters, or 1 byte. And here is a table showing, so you have at the top the most significant bit, and then along the left column is that LSB, least significant bit. And the way you interpret this is you start at the top with the most significant bits, that row of different MSBs, and those 3 bits each represent the first 3 bits of the 7 bits of the number. Or you can think of all those sets of 3 bits with an extra 0 at the beginning, so that you think of it in a set of 4 bits, a full nibble of bits. But that's how you read this chart, is that you start with the most significant bit. Let's just take the letter A. The letter A, if you find that on the table, you look up the most significant bit first, 100. It's in the 100 column. And then you go over to the row across to the left, and you see that the least significant bits are 0001. So the letter A, the full 7 bits for the letter A are 1000001. And that's how you read this table. Other ASCII tables are a little bit easier to read because a lot of ASCII tables have they don't have this column row lookup thing. They just list all the characters with their corresponding decimal representation, their hex representation, sometimes octal. So sometimes a lot of the other charts are easier to read than this, but that's how you would look up these characters. And then you'll also notice all of those abbreviations at the bottom. They're basically just control characters. You have things like, let's see, what's a common one? We have LF and CR. Stands for line feed and carriage return, respectively. And those are often when you hit enter, let's say in Microsoft Word or something, you hit enter and it goes to the next line. Technically, there are characters there. You just don't see them, but those line feed and carriage return characters are there representing a new line. It kind of represents the fact that you're going to a new line. But there are other various, other kinds of hidden characters. A lot of those abbreviations there that they list there are non-printable characters, meaning they don't show up visually when you're typing them out, but they do exist, and they're used for various things. And just the example that I gave about new line characters being carriage return and line feed. The rest of them do other things like that, things that you don't visually see printed on the screen, but that are still there and are still useful. So that's ASCII. That's the ASCII table. And so with just 7 bits or 8 bits, you can represent all of these various characters in just 1 byte. And that's what makes this ASCII code conversion useful, is that you can represent all of these things with just a single byte. Alright, and so then that'll be it for this video. In the next video, I will go over these number system applications.